Optimizing the space to be excavated is a clear objective for the underground construction industry. A new machine developed by Robbins holds the potential to achieve this goal for the civil engineering industry by creating a flat invert in the first pass. We speak today with Brad Grothen of Robbins to know more about the machine, its development, and its application. Welcome, Brad.
Thank you very much.
In the product line and the machines that Robbins has manufactured over the years, what would you say are those that are used in the mining industry and those used in the civil side, as a rough estimate?
Historically, it was a pretty even split. Recently, Robbins has 100% focused on the civil industry, and so we're just now getting back into the mining side. Certainly TBMs have been used in mining, usually on development drifts. Stillwater Mine is a big proponent. They've been using them for a number of years in a few different applications, following the ore body, main ventilation drifts. One notable one is in Australia, where we had the Grothen project, where it's a decline project. In that case, they had to go through some very soft ground, and because of the life of that particular mine, the cost of the segmental lining was worthwhile. Civil tunnels are, life expectancy is 100 years. Very rarely are mines expecting to use their tunnels for that extended period of time. And so really they're much more cost driven in that way. And so they're trying to really refine what's needed.
In those applications, how did those mines create their required flat invert?
They're usually bringing in a separate cast invert piece in order to either backfill it or place a flat invert piece there for their rubber tired vehicles to operate.
But this is still excavating more than they need.
Excavating more than they need, and especially if you're trying to bring in precast concrete, that comes with a notable cost.
But the principal machine of choice is the circular TBM. Mm-hmm. What is it mechanically that makes the circular TBM the most common mechanized tunneling excavation tool?
The interesting part is when you go looking at developing a different way of doing it, you start to really appreciate why a circle was selected. So first and foremost, even if you look at not even tunneling, but other manufacturing processes, a lot of times, anytime you're trying to make a hole, it's using a circular action. So the motion is continuous. As we were looking at bearings, it's easy to seal something like that. So just the action, the rotating action lends itself to a circle. Secondary to that, as we look at the face in tunneling specifically for tools and things like that, I'm able to put a lot of tools on the face to actually excavate the face. They are changing direction and it's scalable. So since I have, disc cutters or scrapers or whatever it may be, I can add on to that relatively easily and grow the diameter or shrink the diameter. So it's flexible, it's scalable, it's easy to seal. And then let's say one more aspect of it is, especially in the rock type cutter heads, you've integrated in the muck removal process. So, how you remove the material from the face is almost as important as, how you're excavating the face itself.
So a machine to excavate a flat invert in rock would have many advantages.
That's our thinking. And so we have some very large machines that have been put into place, 13 meters in diameter, that get filled halfway back up because I want to double or, however many lanes inside of that tunnel. So you're literally trying to achieve the maximum width at spring line. That's the optimization part of the profile that, really brings strength to it.
You were saying that it's quite a high percentage.
Correct. Yeah. I mean, it depends a little bit on what you're trying to achieve, a height and width ratio, let's say, but we're seeing upwards of 50% range. A lot of that is associated with the right sizing of the TBMs themselves. But yeah, it can be quite substantial.
Robbins has developed machines in the past to create a flat invert. I'm thinking in particular of the mobile miner. That was in use. It was a prototype, and several were manufactured in the
80s.
Yeah. What happened? What was that principle, and what happened to that machine?
So the basic principle of that, it was a rotating type drum, which was on a boom, which was able to slew or move around. We had a couple different iterations of it. One just moves back and forth, and one that would create a true horseshoe. It was in many ways like a TBM turned on its end. So you're just cutting with the end cutters. There was some learning opportunities that came out of that. One of the disadvantages with drum type cutters is you're entering the rock at zero, and then you're only really getting full cutter penetration at, let's say the 9 o'clock or at the horizon, then it's leaving at zero. So you're not really getting very efficient excavation. The other aspect is, especially if you slew it back and forth, you aren't having those disc cutters roll in the same track, which when you look at hard rock excavation specifically, that's one of the really key aspects to have efficient excavation. And then finally, it's on the end of a drum. So if you look like a road header, things like that, one of the tools themselves are challenged, but then also you need that stiff load path. And the longer your arm becomes, the more vibration you get, which when you're trying to apply that much power, it's detrimental.
So the new machine creates the flat invert, but is a completely different concept. Is that right?
That's correct. Yep. Instead of having a rotating head, here we have basically a row, some interlaced, but 2 rows of disc cutters, and then we have a slewing head. So it basically oscillates out of plane or up and down.
So it's a partial face excavation model.
Correct.
So what would you liken it to? Is it partial like a road header, for example?
No, I mean, a road header is covering a very, very small percentage of the face. So we're doing full width. And a big part of us doing full width has to do with us being able to always keep those disc cutters in the same track. So if I did a partial width, first of all, I can't advance that heading very far without resetting and go to a new heading. I'm exposing a lot more rock. And so ground support, of course, is always key in tunneling. So by going with the full face, I keep my disc cutters in constant contact. I'm always advancing the heading as a complete heading, and that allows me to apply ground support across the entire profile. So it's not partial face as we'd see in a lot of these different technologies. Certainly not like the MDM, or excuse me, like the mobile miner, which again, we're excavating a very small percentage of the face. Same thing with the road header, a very small percentage of the face. And really what's driving that is a couple of things. First of all, because that's actually cutting the profile, it's cutting the full width. So I need to be able to get some supports, some bearings inside of there in order to actuate the cutter head. And then the secondary part of that is I'm keeping those disc cutters rolling in the same path. I've got a very stiff connection to keep to be able to transmit the power. And then integrated with that head, as it's slewing down, it's transporting that muck. So really trying to pull together several features of let's say, the efficient rock excavation.
Would there be merit in adding more rows of cutters?
The difficulty there is as I'm slewing, so I've got 2 rows of cutters and I've got some gauge cutters. And it's not just going, basically from 6 o'clock to 12 o'clock. In order to engage all those cutters, I'm going well beyond that. So I'm rotating instead of 180 degrees, 220 degrees. And so in order to engage all those cutters to fully cut the rock. So as the height of that cutter head becomes really important, because that dictates how far it has to rotate around in order to fully form the tunnel.
Would you increase the width and therefore the reach of the excavated profile?
We can adjust the width relatively easily. And it's like all TBMs. You ask for a different diameter, we can give you a different diameter. The height is a little bit more of a challenge just because that's set by the distance from the gripper to the end of those disc cutters. And that, basically that's a big moment arm. So that's going to have a greater effect because that has to do with the torque that's basically being applied to the cutter head. But it is a scalable design, just like a TBM.
The MDM5000, it is a large piece of machinery and a powerful piece of machinery. Is that right?
Yes, it's very akin to standard TBMs in that it's applying very high forces, requires a fair amount of power, a fair amount of services in order to excavate that rock and bring it out of the tunnel. One of the big advantages of TBMs is the ability to excavate fast. And to excavate fast, especially in rock, you need a lot of power, you need a lot of force. With that comes weight. So both in the terms of force to react that force and in the terms of power. Power is cheap. In many ways, like torque is expensive and thrust is really what drives the weight. So it's the amount of force that I have to add to the rock in order to fracture it versus just raw power. So it's effective power is more important than just raw power. We can apply lots of power and get very high excavation rates. In the case of, as you go underground, obviously getting that material out of the mine is a huge consideration. So scaling the machine both in weight and power to the resources that are available is something that we're able to do both with the MDM and with conventional TBMs. One of the other aspects to the machine that is key is supporting the ground. It's a mobile factory, so you're continuously supporting the ground, keeping it in place, using live ground support.
What does the machine comprise?
The machine itself is, the current MDM is very analogous to an open type TBM. So obviously the cutting action is quite different. The profile is quite different. But then as we look at the machine itself and then how it manages the full tunneling systems, let's say, it's analogous to a TBM. It's got an articulated shield. So like a open main beam type, you've got the cutter head that does the excavation. And then right behind that is, the cutter head drive. And around that is a shield that's articulated, that is able to expand and come up hard against the tunnel wall. And that does a couple of things. Of course, it stabilizes the cutting action of the head, so it's much smoother. And then it keeps the rock in place so that right behind that ground support can be installed. During normal excavation, it's got 4 drills. 2 of those drills are able to look forward and do pre-excavation type crowding, both outside of the profile and straight ahead in profile.
I understand that Robbins has been working on the development of the machine for a while, and that your prototype is already in action.
Correct. We don't like the term prototype because it's operating. It's not experimental. I mean, this really is designed to build a tunnel. So, but it is certainly the first article, let's say, and it's been operating for a few years now.
Where is it in action?
We collaborated pretty heavily with Fresnillo mine down in Mexico for basically the full development of the machine. So it is designed for a development drift, several kilometers long. And in that way, it's like a typical TBM. So it's bringing all the supporting gear with it, since it's being designed to create a tunnel several kilometers long. When we launched the machine, because it was an active mine, it declined, and that's how they brought out ore from the mine. So we didn't want to obviously stop the mine from operation. So the machine was transported down into 3 large components and then assembled in a very small chamber. So it was optimized to operate in this mine, but once assembled, it's like one solid unit. And then like other TBMs, it's got a few backup gantries, support gantries for all these services that follow behind the machine.
The client in Mexico, did they consider using TBMs?
No, not really. They're trying to go for a very efficient, low-cost tunnel ultimately. And as you start to bring in either inverts or try to have a secondary removal process, compared to conventional, the costs really don't line up very well. So they were very keen to get first pass a flat roadway that they're able to use.
It would be quite a substantial amount of extra material to have to handle in the transportation, the haulage, the disposal. So they must have been looking for this kind of a model from the get-go.
Correct. On all tunnels, transportation tunnels, but all tunnels, that's going to be the case. For this particular mine, because they were working at, minus 600 some odd meters, and all that extra material has to be transported out. And again, that's how they're transporting ore out as well. So there's a much higher cost associated with extra material being removed.
What is its progress?
So it launched back in November 2019. Obviously there's a learning curve like with all TBMs or mechanized excavation, but within the first couple kilometers, they were starting to see 200 meters a month, somewhere in that range. So it's started to see pretty good progress. It then went through several fault zones, and ultimately now it's struggling in probably the biggest fault that the mine has seen since it's started, 40-degree water. And so they're starting to reconsider that original plan with all the seams that it's crossing. Right around those seams is an aquifer, basically, of water. And so that they needed to utilize pre-excavation grouting.
From the operation in Mexico, what have you learned about how you would develop out the concept?
There's been a few things, let's say, that we've looked at. The profile itself has currently has pretty sharp corners on it, and I think that's I hate to say an artifact, but people look at AutoCAD or CAD and say, oh, let's make it square, make it square. Functionally, it doesn't need to be that sharp, and so we're softening those corners, and that's going to help a little bit with the wear on the gauge cutters. So we're changing the radius to be a little bit softer radius. What you would typically more see in the gauge radius of a hard rock machine. The scraper itself, so like I mentioned, as it sloughs down, it follows a fairly complex path because we try to keep full engagement of the cutters just in the direction. So we have a live scraper that helps keep that profile clean. So that's been, let's say, a simpler, cleaner design has been implemented there. And then for stability during reset, we're looking at a live fulcrum. So round machines, sit on a round bottom, right? They sit pretty nice. This is a flat bottom. And so we're basically adding some better leveling mechanisms for the machine to help during reset. It's not such a big deal in very hard ground, but again, as we look at more difficult, softer geologies, it's going to be helpful.
If you were speaking to a potential civil engineering project owner with the same concept, what would be its greatest selling points?
Civil is already a big proponent or user of mechanized excavation. So where the MDM really shines, obviously, is its profile. Its ability to match what's needed for that particular project. And not over excavate it, not bring in all this extra material that you have to remove. And that comes down to cost. What is it that's really needed, and is it a cost-effective way of creating that tunnel?
Would you be looking at, for example, improving the support mechanisms with a precast type liner behind the machine?
That's possible. That technology has been around for a long time. So if you're in very soft ground, I mean, they've had those since the 70s in Japan. So that is to a large extent going to be a function of, what kind of geology they have. Like I said, this is propelling off the walls. So if they're going to have such heavy ground support that they need a precast liner, we might start looking at different technologies there. But again, ultimately it always comes down to the geology.
The client that is using the machine at the moment, what is their feedback?
They so far are quite happy, because ultimately they're getting a lot of the benefit from it. So even when this machine was going through fault zones, our understanding is they were making better advance rates, even though it was greatly reduced than they were seeing with some of their conventional methodologies. So overall, they've been very supportive of the machine. So
where does the concept go from here?
New profiles, really. So again, for us, as an overall development scheme, square profiles work great. We like square profiles. We love round, so don't want to diss round. We've got square, but obviously you see horseshoe tunnels, elongated tunnels. So really, it's this idea of trying to create equipment that is able to optimize the profile for the end use.
Has it created a lot of interest in the industry?
Certainly, yeah. I mean, we've talked to a number of different people, and yeah, there seems to be a lot of interest in it. You have to get in at the planning stages, and people have to say, okay, here's the technology. You have to get buy-in with customers of, hey, here's something new that we're going to put into place. But there has been a lot of interest around, especially the MDM and some of these different technologies. Civil industry is also interested. You have to have a tunnel of a certain length in order for it to be advantageous. And where you see that is in a lot of times railway tunnels, where again, they like flat inverts.
Robbins is known for its innovation and continually exploring new concepts in the field of mechanized tunneling. But where is the industry going in its quest for the best?
Really, it's about cost, excavation rates, and then size, and safety. So one of the things that we always view mechanized as having a big advantage is this idea of continuous support, something that in the civil industry we kind of take for granted. But as we compare it to a lot of the different technologies that are out there, it's not really a given. So really optimizing the profile, creating the safe working environment, and then of course green power, moving towards grid power versus diesel powered, working along with those ideas in a cost-effective manner.
Robbins is well known also in the industry through the decades for producing machines that are powerful, robust, able to stand the test of everything that's thrown at them. In the machines that are being manufactured or designed these days, are the clients compromising on power versus cost?
There's a couple of things going on there. So I think certainly as we look at what's been developed all the years, we certainly are always trying to develop new technologies and apply the right technologies to the jobs. In many cases, the decision on the client side becomes cost driven. So they're trying to balance out a risk versus, reward. And, what do I really need? How much do I really need to put on this project? And so understanding the project, understanding what's really required, and then tackling the difficult projects is kind of the space that we like to live.
Well, it's a really interesting discussion that we've had, and we'll follow all the developments with interest. We'll be back to have another discussion, Brad. Really, thank you very much for today. Thank you.
All right, I appreciate it. Thank you very much.